Let's look at it a little more complicated circuit. Resistor here. We're going to have another one here. Here. And this is point B. This is point A, C, and D. And all the resistors are identical. They're all R. So let's calculate the equivalent resistance between A and B. Equivalent resistance between A and B. So you would connect. That would be the resistance that you would encounter if you try to set up a current between these 2 points, right? If you put a battery here. That would be the resistance of the circuit. Okay? So how do we calculate that? One step at a time. So you look at the circuit and see if you can identify 2 resistors that are either in series or in parallel. Because you know that if you find those, you can simplify the circuit by replacing those 2 resistors with only one. Right? So then you redraw your circuit with that simplification, and then you look again. Is there anything now in series with something else? Is there anything in parallel with something else? Okay? So if you look at this resistor, this one over here, and this one, they're neither in series nor in parallel. We just looked at that situation, right? There is some line connected between them, so that makes them not in series, and they're clearly not in parallel, because you cannot move from one end to the other just moving through a continuous wire. So you don't want to do that. You don't want to try to simplify that one with that one. That's not going to work. You keep looking and see if there's any other 2 resistors that are clearly in series or in parallel. Okay, better. This one and that one, how about that? Are these 2 in series or in parallel? They're not. Not in series, clearly. Current flowing here can split going this way or that way, and they're not in parallel. These 2 sides are connected, but this side is not directly connected with that side. You have to move through a resistor, and that's not good. That doesn't make it in parallel. So these 2 are not. So the only ones that are clearly in series or in parallel are these 2 guys, because there is a current that flows through this one, has nowhere else to go but to move through the other one also. Right? So they are in series. So we can simplify those 2. And how do we simplify it? Well, we replace them. We replace those 2 resistors with one that will do the same job. Okay, so one that would do the same job is one that has R plus R, that's 2R. I'll just erase everything. So I'm going to replace those with 2R here. Correct? If you lost track of what we had before, that's what we had. We're replacing it with that. Okay, so now we have that. Now we look again and see, are there 2 resistors that are connected in series or in parallel? Now that I redrew the circuit. So again, you see that the R and the 2R are connected in parallel. So now you're going to replace those 2 with one that will do the same job. 2 in parallel with 1 gives you what? Quick formula is you multiply the resistors and you divide by the sum. So 2 times 1 is 2 divided by 2 plus 1. Right? So the equivalent resistance of these 2 guys, this and that, they have an equivalent resistance of 2 times 1 divided by 2 plus 1 ohms. So that is 2/3. Right? So now I can replace them with a resistor of 0.66 ohms. And once I've replaced them with that, then the net resistance between A and B is going to be 1 plus 0.66 of R. Right? Because I can replace them, as I said. So I'm going to put here one that has 2/3 of R. I'm forgetting the R here. Sorry, I should include that R. Let's put it here. Times R. Times R. Times R. So this one's 2/3 of R, and this one is R. Right? So now the resistance between A and B, the equivalent resistance, is going to be R plus 2/3 of R, right? Okay, so that's the general procedure. You simplify the circuit one step at a time. Now let's go back to the same circuit as before. I should just erase, it will be faster. That's what we had originally. Now I'm going to do something else. Now I'm going to connect the cable between C and D and ask the same question. What is the equivalent resistance now between A and B for this new circuit where I put that cable between C and D? So what is that cable going to do? Does it change anything? Remember the discussion about shorting an element in a circuit last class? If you have a light bulb connected in a circuit and then you put a wire from one side of the light bulb to the other side, what happens to that light bulb? Does it go out or does it continue shining? This is what I'm talking about. You have battery connected to a light bulb, and now I connect the cable around the light bulb, an ideal cable. What happens to the light bulb? Right. So the light bulb goes out. There's no more light coming out of the light bulb because there's no current flowing through the light bulb. Correct? We know that there's no current flowing through the light bulb because the wire that you just connected there makes sure that point 1 and point 2 will have the same potential. V1 equals V2. If the two ends of a resistor have the same potential, what do we know about the current flowing through that resistor? If you have a resistor and you know that this point has V1 which is equal to V2 at this point, can there be a current flowing through that resistor? The answer is the current has to be 0 because Ohm's law tells you that the current is the result of having a difference in potential. Every time you have a difference in potential across a resistor, you would find a current flowing through that resistor. So if the difference in potential is 0, clearly the current has to be 0. So the current flowing through this light bulb is going to have to be 0 when you connect that ideal cable around it. When you short the light bulb goes out because no current is going to flow through that light bulb. So effectively what you're doing is taking that light bulb, making it irrelevant for the problem. So what is that situation happening in the circuit that we just drew over there? Is there any resistor that has become irrelevant because of the connection of the cable? Clearly the one at on the left of that square has turned irrelevant. There is no current that is going to bother to flow there. Okay, so this might as well not take it out of the circuit. So now, can we continue to simplify the circuit? Is this resistor in series or in parallel with that resistor? They are in parallel, right? Because you can move from here, you can walk all the way here, following a wire, and from this side, you can walk around, following a wire, and end up on the other side of the resistor or the other resistor. So these two guys, this and that, are connected in parallel. Okay? So we can maybe modify that drawing a little bit. Just to make it look more parallel. Right? Remember, changing the shape of a cable doesn't change the circuit at all. Right? Before I had a cable that kind of looked like a triangle Of course, if I change the shape of that triangle, if I move the resistor a little bit along this direction, along the cable, I'm not changing anything in the circuit. Okay, so now those two are in parallel, so now I can replace them with an equivalent resistance, which is going to be 1 times 1 divided by 1 plus 1, so that's 0.5 R. Right? So the equivalent resistance of these guys, these two resistors, is now 0.5 times R. So I can delete them, erase them, and replace them with 0.5 R. Okay, and the answer is now that the equivalent resistance is therefore R plus 0.5 of R, so that's 1.5 R. Okay? Before we got 5/3 of R, right? Before we connected the cable. So connecting that cable obviously has consequences in terms of the total resistance of the circuit.